This module, we're going to look at cloud service and cloud deployment models. Once we understand those, we'll talk about how the responsibilities vary between cloud providers and end users, looking at the NIST deployment reference architecture. We'll wrap up with a discussion of containers and serverless computing, as well as common cloud computing security threats. As we begin to look at some cloud concepts, it's important to understand the different cloud service models and deployment models. So we're going to start here by looking at the possible different service models we have. We can break this down into three main categories that we're going to look at momentarily. You can reference NIST Special Publication 500-322 as a reference guide for these service models. If you want to find out more information, that's a very detailed and thorough document that you can find through a quick search online on the NIST website. So NIST has a cloud computing reference architecture that includes a service layer. Inside this service layer, we find our three service models. We have SaaS, PaaS, and IaaS, software as a service, platform as a service, and infrastructure as a service. Depending on the needs of your business, you may implement one or more of these cloud service models. These services can be implemented and built upon each other as dependent services, or they can be used independently as standalone pieces, again, depending on your needs. Let's begin with infrastructure as a service, or IaaS. Very simply, this is a virtual provisioning of resources that would be available over the internet. This allows you to create virtual infrastructure as opposed to purchasing and implementing physical infrastructure. And that can range from full-blown server implementations to simple data storage solutions. This includes compute, networking, and storage resources. This is a much more economical option as opposed to implementing and managing an on-site data center. You only pay for the resources that you're using, and those resources can be easily expanded or decreased on demand. So you're getting elasticity. Elasticity means that we're able to easily change the size of the resources that we're using. We can expand those services, or we can compress those into a smaller amount of services. Some well-known service providers that you're likely familiar with would include AWS, Google Compute Engine, and Microsoft Azure. Most typically, the users inside of a business who are interacting with an IaaS solution would be system admins. Next is platform as a service, or PaaS. If we are using this in tandem with IaaS, then we're leveraging all of our virtual resources from IaaS for application testing and development. Inside of our business, most typically, we think about developers when we're thinking about interaction with PaaS. PaaS is designed to support the complete web application lifecycle, from building and testing an application all the way to deployment and troubleshooting. PaaS solutions typically have development tools built in that are going to offer time saving for coding new applications. So you can use existing modules or existing code to speed up the development process. And they allow you to easily develop for multiple platforms. For example, maybe if you're trying to have cross-browser support, if you're trying to support multiple browsers, or cross-platform mobile applications, PaaS solutions are great for that. This also allows for numerous users to work on the same application in a very easy, collaborative manner. And we have software as a service, or SaaS. This model gives you quick access to cloud-based web applications. Users here can include anyone, and in fact, as you're watching this right now, if you're streaming this video from your web browser, you're actually using SaaS. You're using software as a service. SaaS very simply can give users quick access to web applications without requiring large downloads or installations on the client side of things. A few common examples of this would be things like Dropbox, Cisco WebEx, and productivity tools such as the Microsoft Office 365 service. Now, as we look at these services, as we move down from the top where we have SaaS to PaaS to IaaS, we have increasing complexity on the configuration side of things, meaning that we need skilled users towards the bottom of this pyramid as opposed to the end users at the top. So the end users are going to have less complexity when it comes to interacting with these solutions. You'll notice that we move from end users to developers down to system admins. And going the other way, we have the increasing ease of use from IaaS to PaaS to SaaS. As we've mentioned, SaaS is geared towards end users where we're serving out end user applications. A great metaphor that I've seen used for these cloud service models has to do with a car. If you think about leasing a car, we can compare that to IaaS. If you've ever leased a car, you care about the model, the price, the specs, the color. In other words, you're going to be the driver. You're paying for the car, you're paying for the maintenance costs, you're paying for the gasoline costs. So it's important to know these things. That's IaaS. PaaS is like renting a car. Let's say you arrive at the airport and you go to the rental desk and you want to rent a car for a few days. You may not really care what color the car is. You're not interested in maybe the performance specs. You just want the car to work and to be reliable. You're paying for that car, but the cost is much less. And you're only paying for the time that you use it, along with the gasoline costs or the usage fees, in other words. That's similar to how we can think of PaaS. And SaaS is like taking a taxi or an Uber. You don't care what it looks like. You don't care about the performance specs. And in this case, you're not even the one driving it. You are not paying the maintenance or the gas costs. That's all included in your taxi fare or in your Uber fees. You just want to get to your destination. That's SaaS. So that's an overview of SaaS, PaaS, and IaaS, our three basic cloud computing service models. Let's now look at our popular cloud deployment models as defined by NIST Special Publication 500-322. This special publication, again, it outlines different cloud service models and deployment strategies. Cloud models are on the rise due to many factors, including the fact that they have distributed storage for data protection, they're easily scaled out, they provide automated management capabilities, and they give us access from any location, among many other considerations. The essential characteristics which NIST outlines for cloud computing are as follows. First, there is on-demand self-service. This means that users can request more resources or services, which will be automatically processed by the cloud infrastructure without any need for human intervention. If you're familiar with Amazon Web Services, that's exactly how this works. You create an account and you use their elastic cloud computing service to create a virtual machine with the resources and the storage that you'd like to use. And then that machine is provisioned for you without any needed intervention from someone at Amazon. If you contrast this with traditional deployment using physical servers and configuration on your side, this is a much faster and more flexible solution using a cloud deployment model. The second characteristic is broad network access. This means cloud-hosted resources are available on a wide range of devices such as PCs, macOS, tablets, and smartphones. This also means that these resources are available from any location wherever there is access to the public internet. The next characteristic is resource pooling. This means that a provider's computing resources are working together in a pool to service multiple customers. This includes not only storage space, but also processor usage, memory usage, and even network infrastructure pooling. It's not feasible to have separate hardware for each customer that is being serviced, and the cost savings offered by resource pooling can be passed down to us as a customer. That's one of the reasons cloud computing is such an affordable solution. Next is something called rapid elasticity. We mentioned the term elasticity in a previous video. Just as we can provision cloud resources very quickly, we can also tear down those instances quickly and easily. If you think about the elasticity of a rubber band, the elastic in that rubber band can stretch out as needed when we want that to fit around something, and then it can snap back to its original form. And this is exactly the same concept. We can very quickly commission or decommission services as they are required. And the final characteristic outlined by NIST is measured service. This means that the cloud provider is measuring or monitoring the services that you're using for various reasons. With some plans, you only pay for the resources that you are using. So this measured service would be necessary for billing reasons. It's also necessary to make sure that you have the resources you need without running out. Cloud providers can keep tabs on your CPU, memory, and network bandwidth to ensure that you are receiving the level of service that you're expecting and paying for. Now that we understand these 5 essential characteristics of cloud computing, let's talk about 4 deployment models. First is the private cloud. In a private cloud, the cloud resources are used exclusively by one client or one business. This private cloud can be hosted on-site, in a company data center, or that can be provided by a third-party cloud service provider. The significant advantage of using a private cloud is the level of security and privacy that we have. If you're familiar with some of the popular compliance models like SOX, PCI, or HIPAA, it's possible to use private cloud services and to still maintain compliance with these industry regulations. Private clouds offer more control and more privacy. Now, the downsides to private clouds are that they are more expensive to deploy because you have to purchase and maintain your own infrastructure, and the customer is responsible for all of the management. You'll see private clouds commonly used with government agencies and financial institutions, any place who values security and privacy over the cost benefits and over the ease of use found with other cloud models. Next is a public cloud model. This is a cloud infrastructure that is provisioned for open use, and this is the most common type of cloud deployment. This is probably what comes to mind when you think of cloud computing, where the resources are owned and operated by a third party, and those resources are shared over the internet. This would include services such as AWS, Azure, and Dropbox, just to name a few. Although public cloud models are extremely cost-effective and they give us great flexibility, it probably goes without saying that the main disadvantage is security and privacy. For the most part, these considerations are out of the hands of the customer, and those are handled by the cloud service provider. Compliance regulation for things like HIPAA and PCI that we mentioned earlier isn't possible with a public cloud because those policies would need to be enforced globally for all of the customers in order for this to meet regulation. Community cloud deployments are a newer variant of the private cloud model with very specific use cases. As an example, there are cloud providers out there who cater to government agencies, only allowing certain agencies to use this service. Because of this, these sensitive organizations can still reap the benefits of shared cloud computing while having the assurance that all users share the same privacy, auditing, and security principles. That's something that would not be possible with a public cloud. The disadvantage here is that there currently are no standards or best practices outlined specifically for community cloud models. As I said, this is still a relatively new type of cloud deployment model that is still evolving, so there are some details to nail down before this will be widely considered most likely. And finally, we have hybrid cloud models. Hybrid cloud models combine 2 or more of the cloud models that we've already mentioned: private, community, or public. This can take advantage of the benefits offered by these different models. So for example, sensitive applications or those with high workloads may be deployed in an on-site private cloud, while a separate public cloud deployment may be used for applications that are less business critical. The initial upfront cost is going to be higher than a public cloud model, and the implementation can be somewhat complex, requiring that we make sure we choose private cloud hardware that is compatible with public cloud infrastructure. So that's a look at the essential characteristics of cloud computing as outlined by NIST, along with the 4 deployment models: private, public, community, and hybrid clouds. Now that we understand the different cloud service models and deployment models, let's talk about the shared security responsibilities for customers and for providers. Depending on the cloud service model that you're using, these responsibilities will be slightly different. We're going to look at a general responsibility overview for SaaS, PaaS, and IaaS, but it's also worth noting that each cloud service provider typically has their own shared responsibility models that are available to customers for their own viewing and consideration. For example, you can find a compliance document online for AWS, Amazon Web Services, and this outlines in detail what their shared responsibility model is. And you can see that here on the screen. And likewise, Microsoft Azure has their own division of responsibility, just as a couple of popular examples. Most cloud service providers will provide this documentation to the end user, so that's something you should definitely reference and be aware of. So first, let's look at the SaaS shared security responsibilities. With SaaS, the customer has the least amount of responsibility, with the provider being primarily responsible for the infrastructure and the software stack. The responsibility for ensuring that the SaaS application is free from vulnerabilities falls on the cloud service provider. Notice that the customer responsibility falls with user security, or in other words, they're responsible for creating and managing their own users who have access, and also who has access to the data. The data section itself does have some shared responsibilities because the cloud service provider does have the responsibility of making sure that any data being input into the SaaS application is secure. However, the customer also has the responsibility of making sure that any data transferred from the SaaS is secure. For example, if you think of this from the perspective of Google Apps, anything that we add into Google Drive becomes Google's responsibility to make sure that the cloud platform is secure, that the underlying infrastructure that that's stored on is secure, and that it can't be accessed by unauthorized individuals. However, if you download files and data locally from Google Drive, or if maybe you share that drive as an enterprise resource, it's your responsibility to make sure that these files are secure and that users have the appropriate level of access. With PaaS, we see the customer responsibility expanding to also include applications. As we've stated in another lesson, PaaS solutions allow for the development and the testing of applications inside of a cloud environment. Again, we see the responsibility for the underlying infrastructure falling to the cloud service provider. The application portion is a bit of a shared responsibility in this case, just as we saw the data portion was with SaaS. PaaS solutions often provide built-in software applications or modules to help develop apps more quickly, and any software applications provided as a part of this PaaS solution must be secured by the provider. However, any software developed within the PaaS solution or using the PaaS solution, that responsibility for security would fall on the customer. And as for IaaS, the customer has the most expanded responsibility set of all three models. This is the most clear-cut distinction of responsibilities, where we can see that the cloud provider is responsible for the security of the underlying network infrastructure. Any applications or data that the customer chooses to run on the infrastructure becomes their responsibility to secure. So if we take AWS as an example, Amazon is responsible for the security of their own cloud, but any virtual operating system, any data, any applications that we choose to host on that platform, we would be responsible for making sure that all of those things are secure. So as you can see, just how much of the shared responsibility falls to the customer side of things is going to depend on the service model that you're using. This is important to understand when you're choosing a service model. If you use AWS for IaaS and maybe you choose to use Azure for SaaS, then you have two different levels of responsibility as a customer, and you want to be aware of that. Also note that these shared responsibilities are in regard to public cloud deployments. If you choose to run a private cloud hosted in your own data center, then obviously all of the responsibility will fall onto you. You would be responsible for the infrastructure considerations as well as the data and applications and services running within that cloud deployment. So that's a look at customer versus provider responsibility in regard to cloud security. These are things you would want to point out for an assessment. If you're performing cloud assessments for a customer, you want to make sure that they're aware of the responsibilities that are going to fall to them in regard to security. NIST also provides a reference architecture for cloud computing that we should be aware of. which describes the overall framework used for cloud computing. This will help us to understand the primary roles and responsibilities further in regard to the standards of cloud computing architecture. If you'd like to read in depth about this and see the full documentation, you can find NIST Special Publication 500-292, and that's going to be the full documentation. This describes the major actors, roles, and functions of cloud architecture. So let's take a high-level overview of this architectural outline. We have our actual cloud provider in the center of this architecture. This is an organization responsible for providing services to other individuals or companies. For example, if we think about providers like AWS or Azure, these would be found here as organizations that are actually delivering cloud services through network access. Inside of this layer of the architecture, we would see, of course, the service layers that we've looked at previously. For SaaS, the provider controls and manages the applications and the infrastructure for the cloud consumers, with the end users having limited administrative control. For PaaS, they manage the infrastructure and they provide support and tools for the development and deployment of applications. So they'll provide software development kits or SDKs, or maybe integrated development environments known as IDEs. For IaaS, again, the provider hosts the underlying resources, such as the servers and the storage, and also the network infrastructure. The customer would, of course, be able to use this in various ways, having the most level of control over their virtual resources and what they're using on this service. Also here, we have a layer called resource abstraction and control. This is a concept simply meaning that the provider is managing access to the physical compute and networking resources that they are providing to the customer. So in short, the provider is managing and providing reliable usage to the consumer. We also have the physical resource layer as well, which would include the underlying hardware resources that are owned and maintained by the provider. This would be network infrastructure that you would typically think of, such as switches, routers, firewalls, and so on. And that would also include hardware resources as well, like memory and CPU. Other considerations related to this would be facilities resources, maybe the ventilation of their server room, the temperature control of that room, and power failure handling. So basically, this is the management and maintenance of the entire physical infrastructure that they use for hosting their services. We also see cloud service management here as well. This encompasses everything that is service related in regard to the way that the provider interfaces with the customers. We see business support capabilities, which would include accounting, pricing, and general customer management. We also see support with provisioning and configuration, meaning that they are monitoring resources and ensuring that the customers are receiving the service they are expecting and paying for. Service level agreements, or SLAs, would come into play here. As a cloud consumer, we have certain expectations regarding things like the availability of our services and the performance of what we're paying for, and those expectations are outlined by the cloud service providers in an SLA agreement. Also, the cloud provider is responsible for ensuring that their services are portable and interoperable. This means that we can access the data easily, to copy data or maybe to bulk transfer that away from the provider if necessary, and also that there is a unified management interface that allows us to affect our service. And of course, cloud providers have expectations that they must meet in regard to security and privacy standards as well for their paid services. We've mentioned the cloud consumer, and we see that entity in our architecture as well. So very simply, this is any customer using services provided by a cloud provider. Those can be SaaS, PaaS, or IaaS, or any combination of those. We also have an entity called a cloud broker. As cloud computing has matured and expanded, we've seen a rise in cloud brokers. These responsibilities were traditionally handled by the cloud service providers themselves. But as we've seen demand grow, we've actually seen this entity grow in popularity as a necessary tool to meet demand. So this is a newer business model for cloud services. Oftentimes, cloud brokers can be used to bridge between on-site services, maybe like an on-site data center, and a cloud provider. And that can create things like hybrid cloud deployments that we've talked about in a previous video. Kyndryl is an example of a cloud broker. They actually branched off from IBM as a way to integrate cloud services from multiple cloud providers in a hybrid manner. So it gives you a unified way to affect multiple services. There are, of course, many examples of cloud brokers out there. This is just a popular one that I wanted to point out. Cloud brokers are something that you may or may not see depending on whether or not you're using a single cloud provider or a hybrid cloud model, and also depending on whom you've signed up with service through. If you've went directly through somewhere like AWS or Azure, then you're most likely not using a cloud broker. At the bottom, we have the cloud carrier, which acts as a connection between cloud consumers and cloud providers, and that happens through network or telecommunications. That can also provide a connection between cloud consumers and cloud brokers as well, if that's relevant and being used. These would include traditional telecom and internet providers that we would think of when we're connecting any sort of WAN. And then we have a section for cloud auditors as well. This is the role that we will generally take as ethical hackers when we interact with cloud consumers. We perform audits against systems to ensure that security, privacy, and performance are all acceptable. We're examining security controls, we're checking for vulnerabilities, and also making sure that the cloud consumer meets any industry-specific regulations that they are required to meet, both from the standpoint of privacy laws and also things like PCI or HIPAA compliance. Container technology is an emerging trend in cloud computing, so let's talk about what container technology means. The traditional approach to virtualization was through virtual machines, and these are certainly still around and in use. They're very popular in the home as well. I actually run virtual machines myself in my home lab. With a virtual machine, one set of physical hardware, maybe a single physical server, is able to host multiple virtual machines. Each of those virtual machines will have its own operating system along with its own applications. So we may have various operating systems and apps running virtually on a single physical device. Now, this does create a lot of overhead, and it's generally considered to be inefficient these days. In contrast, we now have containers. This isn't necessarily a new technology, but it is becoming more popular. These work as a package of application and software, and that would include all of the library files and other dependencies bundled in. These containers run on a single operating system, the same operating system as the underlying server, and each container shares the single operating system with all of the containers on the server. So in general, this means that containers require less resources than virtual machines, and they're much more efficient. In terms of storage, if you're familiar with virtual machines, these can require many gigabytes of storage. Because we're running multiple virtual VMs, each of those VMs has their own host operating system and their own applications, their own library files, and so on. Even if they're all running the same operating system, this still requires every VM to have its own storage, while containers may only need a fraction of the storage space. Many VMs are going to require several gigabytes, while a typical container may only need a fraction, maybe down in the megabytes range. One popular example of container technology is Docker. Docker is essentially a container engine that uses Linux as the underlying operating system. This is installed onto a server, either virtual or physical, and it allows us to deploy separate containers sharing the resources of the underlying Linux host operating system. Kubernetes is another example of this, originally developed and designed by Google. If we look at a visual representation of this, you can see the differences in VMs and containers. Each deployment model has its own pros and cons, of course. So with VMs, you do have the ability to run various operating systems from a single server, which may be more efficient for your needs. Of course, this will require more storage, as each individual VM is going to need its own operating system files and libraries, even if they're running the same operating system inside. So if we have 3 Windows virtual machines, those are all going to contain their own Windows operating system, meaning that you need storage space for installing Windows 3 times. With containers, the underlying operating system is virtualized, and that's shared out with the containers themselves. This means that the containerized applications are going to believe that they have the operating system installed, as well as all of the underlying resources like the memory, the storage, and the CPU. So containers are more lightweight because they don't require individual operating system libraries, but they are of course constrained to that underlying operating system. In other words, they have to run whatever the underlying operating system is. You can't mix and match here. If we have a container for Windows, that can't run on an underlying Linux operating system, and vice versa. With all that said, there are some specific security considerations in regard to containers that we should be aware of. First is they present a challenge with isolating resources. Containers need to communicate with one another in order to perform properly, so it may be difficult to implement firewall or network traffic control rules that properly secure our containers while still allowing them to function as we would expect. This could allow attackers to escalate privileges or even access the underlying container host itself. For this reason, we want to make sure we have the ability to restrict communication between containers to only that which is necessary for operation. Now, the good news is most of this is simplified with many container technologies. They have the ability to isolate containers in this manner, such as Kubernetes. Another concern is the larger attack surface presented by container technology and by virtualization in general. By having many applications or operating systems available, or even multiple virtual machines, we're creating more potential for malicious entry. We want to make sure that we are decommissioning any unneeded containers. Containers themselves are something that are easily and quickly moved around, deployed, and then decommissioned. So we think of these much more temporary than we would a physical server. For that reason, when we're finished with a particular resource, we want to make sure that we delete it and make sure it's not running in the background, unchecked and unmonitored. Vulnerable source code is another concern. Many container technologies are open source solutions. Kubernetes that we mentioned earlier being one of the most widely used free and open source container management systems. Open source code in general is considered to be more susceptible to vulnerabilities. So we want to be especially vigilant with auditing and monitoring these open source solutions. And visibility is also a concern. By using virtualized technology, we're adding more layers of complexity into our network topology. This in turn means that there are more things that we need to keep track of, and that means there are more layers of potential obfuscation between attackers and our monitoring systems. Other main concerns with securing containers include those implemented during the deployment. We want to make sure the host container itself is properly secured from the perspective of software updates and also from the perspective of network security. So our general considerations for any server asset would apply here. We want to make sure our operating systems are up to date, that we have good firewalling rules in place, that we're closing unnecessary ports, and so on. There are many different monitoring tools available also specifically made for containers that you may consider implementing if you use container technology extensively. The one I'll point out here is called Prometheus, and you can find that at prometheus.io. This is a way to gather information in real time to identify anomalies, and it also has alerting features as well. This is probably one of the most widely used monitoring tools for containers, but there are certainly many others available that you might consider if you use containers extensively. Serverless computing is another fairly recent advancement in cloud technology that we want to be aware of. The main difference with serverless computing is that from the customer perspective, we are not tasked with provisioning or maintaining anything from the server side of things. That would include the underlying server hosts and operating system for the things that we're running. I should also note here that the name is slightly misleading. This is not a completely serverless architecture from the physical network standpoint. When we say serverless, we're simply referring to the fact that the underlying servers are not exposed to the end cloud consumer. There are obviously servers in use here, but they are of no concern to us and they're out of our reach as the end user. The cloud provider themselves would be responsible for all of the server resources that we're using, including the provisioning of resources, the maintenance and patching of those resources, any traffic load balancing that is needed, security and privacy for the infrastructure, and so on. Serverless computing introduces an additional cloud service model, in addition to SaaS, PaaS, and IaaS that we've already looked at. This introduces something called Function as a Service, or FaaS. To contrast this with PaaS, if we're using PaaS for application hosting and development, we have server processes that are constantly running. That means that we are paying for those resources, even if we're not actively interacting with them, even if we aren't actively developing on the PaaS platform. Although FaaS does most closely relate to PaaS, in contrast with that, FaaS solutions allow us to simply upload code into a cloud provider's environment without provisioning any underlying server or development platform. So this is primarily a development tool that's used. The cloud provider would take care of all the back-end work for us, and we can execute any code that we've uploaded on demand. Whenever that code is not actively running, we are not being charged. So let's outline also a few differences between serverless computing and containers, because you may be wondering what the difference is there. We've already mentioned that the difference in provisioning and maintaining the underlying servers is the main consideration, but we also have scalability. With a container architecture, we have to determine our resource needs ahead of time. When we create a host server to support our containers, we need to take into consideration how many containers we're going to deploy on the host operating system, the resource needs of those containers, and more. With serverless computing, this happens in an on-demand manner, and all of the scaling happens on the cloud provider side as needed. Maintenance is also a place where these services differ. The maintenance of containers falls to the customer who has deployed the container in the cloud infrastructure. With serverless computing, there is no back end to manage from the customer's perspective. We would simply deploy some sort of code into a serverless computing solution, and then all of the maintenance and patching of the underlying infrastructure, of course, falls to the cloud provider side of things. And one last one I'll point out is the overall cost. That could be much lower with serverless computing. With containers, these are constantly running on the cloud, and we will be charged for the storage space even if no one is accessing the container resource. Serverless architecture typically deals with code that is executed when it's invoked. That's the common way we use serverless computing. So that means that when the code is not being invoked, or in other words, when it's not being interacted with in any way, it essentially doesn't even exist as a resource. The code is not running, it's not consuming resources, and therefore we are not paying for that all of the time. Let's look at Amazon Web Services as an example of this. Their serverless computing solutions are among the most popular in use today, and there are of course many others out there such as Azure and Google as well, but we'll take AWS as an example here and look at some of their services. AWS Lambda is the main general purpose serverless compute engine used on AWS. Lambda allows developers to run coding inside of AWS without the need for provisioning any servers. That also means that there are no servers, of course, for us to manage. Lambda is constantly updating their support for different coding development platforms, and at the time of this recording, they support Java, Go, PowerShell, Python, C#, and more. So it is extremely flexible. From a very basic standpoint, how this may work is, let's say that you upload your code to AWS Lambda, and then you would specify the amount of memory that you need for the function of the code. When that code is invoked, those memory resources are provided to the code, and the code is executed. Whenever the code is not being invoked or triggered, then the code is not running anywhere, and it's not consuming resources. So this is a pay-as-you-go model, where you're only paying for the resources being consumed and the amount of time that they're consuming those in an on-demand manner. And of course, as we've mentioned, there's no need for us to provision or manage any underlying host or server resources. It's very simple and it's very fast. One of the limitations to be aware of with Lambda is that there are certain quota limits to code execution. For example, there's a 10 gig limit on memory allocation, and the maximum runtime for code is 15 minutes continuously. And there are other quota limits outlined in the AWS Lambda documentation as well. So for those reasons, you might want to choose another option if you need more resources, or if you have a more robust process. Lambda is really for simple tasks and simple development. One of those other options is AWS Fargate. Fargate is Amazon's solution for running Docker containers. Again, though, we have no need for server management with this serverless solution. If you think about deploying Docker containers yourself, you would of course have to provision a host operating system and deploy those containers into that. Now, there is some confusion sometimes between Lambda and Fargate in terms of which service may be the right one. So in short, if you have a Docker container that you want to deploy, if your application is sensitive to latency, or if you need support for high traffic and higher compute resources, Fargate is going to be the better option. It's going to be more robust for serverless computing, whereas Lambda is more temporary and designed maybe more towards testing and development of code. One more simple example of serverless technology is within AWS S3. S3 is their simple cloud storage solution, and buckets are their term for containers. Buckets are going to contain objects, and objects can be any sort of file that you'd like. A simple way that this might be used is hosting a static website. If you're building a website for internal testing or internal development, or maybe a website that you simply don't expect to receive a lot of traffic, you can drop those website files inside of an S3 bucket. Let's say you have coded HTML pages. You could drop those in an S3 storage bucket, and after you do that, there's a very simple point and click option in the S3 bucket configuration, and this gets turned into a functioning website. These websites can even be cached around the world in Amazon servers, which would provide super fast and responsive web pages. So very quickly, very simply, you can get a static website up and going using a serverless technology like AWS. In regard to some security considerations that we want to be aware of for serverless computing, you should realize that since the backend is out of our reach and out of our control, obviously our trust is in the vendor to maintain security and privacy. So you definitely want to choose a trusted and well-established vendor. Since we are not being assigned our own dedicated server resources, we're sharing those with a large amount of tenants, in other words. I would not recommend using anything in a serverless manner that may gather personal or sensitive data of any kind. Serverless computing is a great place for application and code development, but you want to make sure that you take care with how you implement your actual enterprise assets within these solutions. Just as with other topics we've looked at, OWASP outlines the top 10 cloud security risks in regard to planning and deploying a cloud environment. So let's examine each of these threats. Number 10 is non-production environment exposure. When we think of non-production environments, we typically mean staging environments used for application testing. These are typically less secure, usually just to make those easier to use rather than having our users jump through security hoops. A common problem we see here would be reused or default staging credentials in place, which creates a risk. For that reason, it's recommended that we avoid using any real or sensitive data in our staging environments. And of course, we want physical controls in place as well to ensure that anyone with access to these environments has authorization to be there. So for example, you would want to keep your staging environment behind a locked door, requiring maybe keycard access that only legitimate employees would be able to access. Cloud infrastructure security is number 9. Behind every cloud solution is an actual physical infrastructure somewhere, and that would include storage, hardware, networking, and even virtualization. We should follow typical industry guidelines for any deployed infrastructure here, securing the underlying networks and the hardware appropriately. Our traditional security measures are considerations as well, such as properly updating and patching systems, and also regular vulnerability assessments. Misconfigurations are one of the main ways that attackers are able to perform reconnaissance and scanning against our cloud computing environments, and that would leverage infrastructure weaknesses. Number 8 is incident analysis and forensic support. With any security event on our network, the first place we would turn during an investigation would be the log files. With a cloud environment, this can present more of a challenge, especially if we're working with a third-party cloud provider who is servicing multiple customers through shared resources. For this reason, we need to thoroughly understand the cloud logging process and be familiar with evaluating the logs for our resources. This awareness should be in place before any security event. You don't want to discover that you have restricted logging or maybe not enough logging taking place after you have an issue. The way your cloud provider handles, stores, and correlates logs should be a consideration during the initial phases of cloud environment deployment. You may also want to consider cloud-specific logging solutions if those are appropriate. These solutions can actually be placed inside your cloud environment as a virtual machine to gather logs that you have immediate access to, and which you can configure for your own level of visibility into the cloud infrastructure that you're using. Number 7 is multi-tenancy and physical security. In cloud computing, multi-tenancy refers to shared hosting, where server resources are separated between different users. Ensuring that your chosen cloud provider has adequate logical separation is something else that you should consider when you're choosing a cloud provider, or if you're planning to host your own multi-tenant cloud. Encryption technologies like virtual private cloud, or VPC, can also prevent shared infrastructure problems. For example, Amazon VPC allows you to essentially create separate VPC subnets that would restrict access between cloud web servers and applications. Next, we have service and data integration. The nature and convenience of cloud computing means that we have data flowing between end users and a cloud environment, typically over the public internet. To lower risk and to protect information confidentiality, we should use data encryption protocols like SSL or TLS. VPNs may also be a consideration here. The main goal is to ensure that our data that's being passed in transit is not able to be intercepted and interpreted by unauthorized parties. Next, we have secondary usage of data. In general, when we place our data into the cloud, we should realize that we're giving up some control of that data. You may not even realize that this is happening, but this is often outlined in the terms of agreement that we'll typically just glance over before we accept. If you think of most social media websites as an example, most of those will default to sharing most of your personal information unless you specifically configure that to do otherwise. So we want to make sure our cloud services aren't doing the same. We want to check with our cloud providers specifically to see how they handle data and to make sure what they do or do not collect and share for secondary purposes. Next, we have continuity and resiliency. This means that our processes, our applications, and our cloud infrastructure that we're using should be available even during the event that there is an unforeseen disaster. In other words, we want minimal downtime and we want redundancy in place. Not only that, but cloud providers should have appropriate disaster recovery methods to recover from catastrophic events, maybe such as a natural disaster. These considerations are going to be outlined in our SLAs, our service level agreements. Those are something we've talked about previously. These define what steps the provider is agreeing to take to ensure that we have continuous availability and resiliency to recover from any unfavorable situations. Next, we have regulatory compliance. If we're working in an industry that falls under specific regulatory compliance requirements, such as PCI or SOX or maybe HIPAA in the healthcare industry, then this would certainly be a concern when we're using cloud resources. One of the main considerations for ensuring that we are compliant is the physical location of our data. The reason being that data storage privacy laws can actually vary between countries. So we should choose a cloud provider that's willing to be transparent about their data center locations. Depending on where that may be housed, you might not be under your compliance regulatory model, so you may need to choose a different provider. We should also consult our cloud provider with any concerns regarding the regulations that we do need to meet. We want to make sure they understand our needs and that they're able to meet those appropriately. Number 2 is user identity federation. Ensuring our users are authenticated and authorized properly, that's not unique to cloud computing, but there are often complications here because we have the need maybe for creating separate login credentials. A best practice recommendation is to create some sort of single sign-on implementation, or SSO. This is what we call identity federation. Federation meaning that we're trusting authentication across domains or across software in a seamless manner. Now, this might seem counterintuitive because we have only one login credential set, but this is actually considered more secure because then we can use a single, stronger password for an easier end user experience. This also creates less management for the internal IT team because we have less credentials to lose track of or to reset. And of course, this also ensures that our credentials are handled internally. We're not relying on the cloud provider to manage those for us. We have control of those through our single sign-on solution, and that gives us better control and better ability to ensure that we have proper user authentication. And the number one identified threat to cloud computing is accountability and ownership. We've mentioned that cloud service providers have partial or full control over your data, and you granted that when you accept the user agreement. But we also need to understand that although we may be using cloud infrastructure, we should not solely rely on the cloud providers for the security of our data. In a previous video, we examined the shared responsibility models, and this number one identified threat to cloud computing is the reason that we need to understand those. We need to make sure that we know our role in regard to the security of our cloud data. In regard to cloud computing, many of our typical hacking methods are still going to be relevant here as well. Specific attacks such as social engineering and network sniffing attacks are certainly going to be relevant, and we've looked at those in regard to non-cloud environments. Also, session-based attacks are relevant when interfacing with cloud resources in a browser, such as SQL injection and cross-site scripting, and certainly various forms of denial of service attacks. There are some additional hacking techniques specific to cloud environments that I do want to mention here for completion, starting with something called a wrapping attack. Wrapping attacks are a type of man-in-the-middle attack, and these are also referred to as XML signature wrapping attacks. This is commonly seen against SOAP message exchange, one of the web services we've looked at previously in this course that uses XML, extensible markup language. When a user exchanges messages with a cloud web server, they send a request over to the server. The server is going to respond with a SOAP message containing a header and a body with the requested information inside. With a wrapping attack, an attacker actually intercepts the SOAP message before that reaches the user. The XML signatures on the messages ensure that the messages are being generated by authenticated users. So the attacker will actually leave all of this in place, and they will append additional malicious content to the original SOAP message. This then gets sent back to the cloud server, allowing them to potentially run the malicious code attached to the original message or to gain access to the cloud resources. Another type of cloud hacking technique is a cloud hopping attack. These attacks are specifically targeted at MSPs, managed service providers. These will have numerous customers that they service. This made news in 2020 when such an attack was performed against at least a dozen MSPs in the United States and Canada, including IBM. MSPs make an enticing target because they have access to dozens or maybe even hundreds or thousands of individual organizational networks and data through the cloud services that they may be providing. This works when an attacker is able to gain access to an MSP in some way through one of the techniques that we've looked at in this course. The remote access they gain can be used either to gather intelligence about all of the MSP customer data or to directly contact these customer networks. With data gathering and reconnaissance, they may use this information to perform spear phishing campaigns against the MSP customers, or they may be able to obtain information about login credentials for these customer networks in some way, or obtain other types of sensitive data. Alternatively, they may also directly contact these customers through the access that the MSP has with remote access, attempting maybe to install malware for their own backdoor access, or maybe they're trying to steal data on the local customer networks or even perform denial of service attacks. Another one is MITC, man-in-the-cloud attacks. These are another form of man-in-the-middle attacks specific to cloud computing. The majority of popular cloud services, like Dropbox or Google Drive, those are going to save an authorization token on a user's device, after the initial authentication is completed. So you may install an application like Dropbox, you're authorized, and then you have an authorization token. Essentially what this means is that we don't have to re-enter our password every time we access the application. We use that token to prove that we have authorization. So it's a convenience measure for us as end users. As long as the token is legitimate, most cloud services don't care which device the token has originated from. This means that if an attacker can obtain and copy one of these tokens, then they can access the cloud resources and appear as a legitimate user. This, of course, requires gaining access to a user's system in some way through malware or maybe social engineering. Once that token is obtained, then they can access the cloud resources without ongoing access to the user's system. And the last one I'll mention is a man-in-the-browser attack, or MITB. This is another type of man-in-the-middle attack. In this instance, an attacker has infected the victim's browser with malware that has the ability to exfiltrate data back to the attacker. Many cloud services are accessed through a web interface. So that means that when the victim logs into their cloud services, the data is exfiltrated back to the attacker, giving them legitimate login credentials to the cloud resources. As you can see, many of these cloud hacking techniques involve manipulating an end user in some way through malware infection or social engineering. So the first major consideration here for protection is, of course, user education. We've mentioned this extensively already. We've outlined the importance of making users aware of things like phishing emails and suspicious websites, among other things. Next generation security appliances can help as well, such as intrusion prevention systems, which may detect these interception attacks. And of course, all of these hacking techniques underscore the importance of privacy measures such as VPNs, which can protect our data from eavesdropping. Let's talk about some important cloud security concepts now. We've already talked about the shared responsibility model and how that is relevant, so we certainly need to understand our role in the various layers of cloud security. If we examine a popular security control model and map out our cloud layers to that, at the bottom we have the physical layer. If you're a cloud end user, this responsibility falls to the cloud provider. If you're hosting your own cloud environment, whether that's for internal employees or for external customers, then this would obviously be a concern for you. Considerations here relate to physical security, meaning that we want to prevent unauthorized individuals from gaining any physical access to the underlying infrastructure. So your traditional physical security measures would apply here. Things like door locks, RFID card readers, security personnel, and security cameras, and so on. The next layer is the compute and storage layer. Here, the concern is the protection of the physical compute resources and the devices storing the data and, of course, the data itself. In a traditional sense, we think of these as the actual physical servers in the data center. These compute and storage resources should ideally be protected by firewalls and next-generation security devices like IPS, intrusion prevention systems, which are specifically host-based in regard to their protection mechanisms. It's also important that logging is happening here for a historical record of events on these devices in case we need to perform security auditing at a later time. As for the data itself, encryption can obscure the data from any unauthorized parties, and we also want to make sure that we have backup and recovery mechanisms in place as well. In the event that data from the storage is lost or otherwise damaged, there should be a backup and recovery system in place to ensure that cloud consumers have resiliency and availability for their services. This is something that we've talked about previously. The next layer is something called trusted computing. This means that we have secure software and APIs in place. APIs, or application programming interfaces, are a way that we enable applications to exchange data securely. There's also a concept called ROT, root of trust. These are a set of functions that will always be trusted by the underlying operating system. So ROTs can help prevent things like rootkit infections, and they also aid in data encryption. The next layer is the network layer. This layer will contain all of our traditional network security considerations that would be relevant for any network. Things like network-based firewalls, IPS, and other next-generation security devices. Proper design is important here, such as using network segmentation through things like DMZs in place. We want to have proper subnetting and routing considerations as well. We might consider quality of service rules and more. So in short, we're concerned with protecting the network from outside access in an unauthorized manner. And we're also concerned with protecting that from things like denial of service attacks. Next is the management layer. The management that we're concerned with would include user management, patch management, and configuration management. Mechanisms like IAM, identity and access management, those allow us to authorize who has access to certain cloud resources and the actions that they are allowed to take. This is something that we commonly see in places like Google Cloud. They have an identity and access management module. When we're talking about patch management, many cloud platforms allow you to perform patch compliance scans to see if anything in the environment is not currently running the most recent patches. That would be in regard to your VMs or even your software that is deployed in the cloud. They can also provide scheduling and installation of those patches in an automated manner. And similarly, configuration management allows for automation regarding the deployment of software packages, VMs, or operating systems. With all of our management practices, the most important feature of these systems is the ability to monitor the status of our management services and also to monitor those with historical logging, again, in case there's a need for security audits at a later time. Next, we have the informational layer. This is, of course, where information would be presented to the cloud end users. Here, we're concerned with protecting this data from unauthorized parties through means like encryption. So, for example, using SSL or TLS connections for the end user. Those will protect the sensitive data that they're accessing from eavesdropping or man-in-the-middle attacks. Also, many cloud providers have a built-in DLP functionality. DLP meaning data loss prevention. The goal of a DLP system is to prevent the leaking of sensitive data through protection mechanisms. Cloud providers like Google have the ability to automatically detect sensitive data, such as social security numbers as an example, and they would alert administrators of any instances where this data may be contained in your cloud environment, so that these administrators would be aware of the risk and be able to take appropriate measures. This is another place where logging and monitoring is important, so we can see who has accessed the resources and exactly which resources they were trying to affect. And finally, at the top, we have the application layer. This is the actual end user's interface with which they're interacting. The OWASP web application standards and protections would apply here. We've talked about those common threats to web applications previously, and we should have an awareness of all the common weaknesses that we've looked at in this course. It's important also that we're performing ongoing vulnerability assessments against our web applications in order to protect this application layer. I also want to point you to a few tools for performing vulnerability scanning against cloud platforms. Cloud platforms can be extremely complex and involved, and there are many options out there depending on your service provider and the service model that you're using. So these automated tools can really help bring things into focus. First, we have a tool seen here called sysdig. If we look at the products menu found at sysdig.com, you can see all of the available cloud platforms that this works against. And it works against many of the most popular ones, such as AWS and Google Cloud as a couple of examples. Sysdig can automatically scan your cloud environment and create an inventory of all your assets. And then it would check those assets against the CVE database for any known vulnerabilities associated with your deployed containers. Another tool that I'll mention is an online resource called Spice. This is a general IP and domain enumeration tool similar to others that we've examined previously in this course. One of the things that we can do here is we can actually enumerate S3 buckets. You can put in your own domain or IP address here, and you can enumerate any S3 buckets that you may have to see if any of those have been misconfigured in any way, which would leave you open to exploitation. If you're using AWS and S3 buckets, this is a great way to check out your environment. You can, of course, also find various other S3 scanners on GitHub, such as this one that we see here, simply called S3 Scanner. This looks for open S3 buckets and can even dump the contents. There are also container-specific tools, like CCAT that we see here, the Cloud Container Attack Tool. And there are even tools specifically for Google Cloud, such as the GCP Bucket Brute. This will attempt to enumerate Google Cloud storage buckets, and it will also attempt privilege escalation against those buckets. Similar to AWS, Google Storage also uses buckets for file storage. There are, of course, many more tools out there depending on the cloud environment provider that you're using, but I wanted to give you an overview of some of the available tools for performing security assessments against cloud environments.